Let's talk about a measure of clustering. When we introduced the correlation coefficient, we said that the correlation coefficient measures how clustered the points are about a straight line. We can now quantify this statement. Let's talk about the standard deviation of the fitted values. We know that the slope of the regression line is r times the standard deviation of y divided by the standard deviation of x. And this implies that r times the standard deviation of y is the standard deviation of x times the slope of the regression line, just by cross-multiplying. But now the fitted values, the values that we're predicting, vary because x varies. And changes in x result in changes in the fitted values by the slope of the regression line times those changes in x. So the standard deviation of the fitted values is the absolute value of the slope of the regression line times the standard deviation of x. That is, the changes in the fitted values have size equal to the slope of the regression line, or the absolute value of the slope of the regression line, times the standard deviation of x. And the slope of the regression line in absolute value times the standard deviation of x is r times the standard deviation of y, just given by our formula on the second line of the slide. So this says that if we take the standard deviation of the fitted values and divide by the standard deviation of y, we get the absolute value of the correlation coefficient. And this is an important formula. In particular, if you square both sides of this bottom equation, we get the variance of the fitted values divided by the variance of y, and that should be equal to r squared. The variance has weird units, but it does have some good mathematical properties. And one of the good mathematical properties is the following, that the variance of y is equal to the variance of the fitted values plus the variance of the residuals. If we take this red equation and we divide by the variance of y, what we find is that on the left side we get 1, and then on the right side we get r squared for the first term, plus the variance of the residuals divided by the variance of y. And if you solve for the variance of the residuals divided by the variance of y, you see that this quantity is 1 minus r squared. This tells us how the residuals vary as a proportion of the variance in y. Now, if we take this equation and we take the square roots of both sides and cross-multiply, you get that the standard deviation of the residuals is equal to the square root of 1 minus r squared times the standard deviation of y. We know that the average of the residuals is always 0. Now we're getting a handle on the standard deviation, or the spread, of the residuals, and that spread is a function of both the correlation coefficient and the standard deviation of our y values to start. Let's move over to the demonstration. Here we've got some functions that will compute the correlation and variance for us. And in the first line, we're computing the correlation of length and age in the dugong data. And then after that, we're computing the standard deviation of the fitted values for age divided by the standard deviation for age itself. And what we see is that the absolute value of r here matches up exactly with this quotient of the proportion of the standard deviation in the age that's explained by the fitted standard deviation, by the predictions that we make. It's more common to talk about the r squared value, and if you compute r squared here, you get 0.68, a little bit more, and that r squared value is exactly the same as the proportion of the variance in the response variable, variance in the age, that's explained by the model itself, by the predictions that we're making. So we're explaining almost 69% of the variance in age that we're seeing by our predictions. As explained previously, the variation in the residuals is what's left over from the variation in y. And if you, again, take the variance of the residuals and divide it by the variance of the age, you find you get 1 minus r squared here. And this is a statement about variances, but we could take the square roots and get a statement about standard deviations. And we can find that from this that the standard deviation of the residuals is the square root of 1 minus r squared times the standard deviation of the ages of the mammals. Let's go to a discussion question that we can find on the PowerPoint. We're returning to the situation with the midterm, where there was an average of 70 and a standard deviation of 10, and a final. In this case, the average is 60 and the standard deviation is 15. And we happen to know that the correlation coefficient for student scores on the midterm and student scores on the final is 0.6. We'd like to fill in the blank for this statement. For at least 75% of the students, the regression estimate of the final score based on midterm score will be correct to within a certain number of points. Think about this question, pause the video, and then resume when you've got an answer. Okay, let's talk about the answer to the discussion question. The question asks us to ensure that 75% of the predictions are accurate to within a certain range. We need to find that range. We focus on the residuals. Chebyshev's theorem says that 1 minus 1/2 squared, which is 3/4, 3/4 of the residuals are within 2 standard deviations of their mean. And their mean is 0, right? So we look for, and that's the 75% that we were talking about in the question. So we're looking for the standard deviation of the residuals in order to get a sense of how wide this interval should be. And the correlation coefficient is 0.6. So the standard deviation of the residuals is the square root of 1 minus 0.6 squared times the standard deviation of the y values. And the y values are the final exam scores. And the square root here turns out to be 0.8, and the standard deviation of the final exam scores is 15. So we get 80% of 15, which is 12 points for the standard deviation of the residuals. So the errors have standard deviation 12 points, and that means that we know that 75% of the predictions are within 24 points, 2 standard deviations of the residuals. That's a pretty wide interval. The interval itself, since it's plus or minus 2 standard deviations of the residuals, the interval itself is twice as big. It's 48 points big. That's probably too big a spread to really draw any firm conclusions about anything. But if you wanted to get a smaller spread, you'd either need to have a better correlation, a higher correlation between the final exam scores and the midterm scores, or you need to have smaller standard deviation on the final exam itself in order to get a narrower interval.